Okay, cool. Hi guys, so let's begin our today's recitation. So these are your favorite TAs, Hannah and Carnegie, and hi Nat. Yeah. Okay, let's begin our recitation. So this recitation is about recurrent neural networks. As you have studied in this week's lecture, let's first go over what is the definition of this RNN. So a recurrent neural network is like this, the left part. So each time step, it will input xt here, and then it will use the information it stored for the past input, and then times this matrix W with its st-1, and output is here. So we just like, so the right part is the unfolding part. So in each time it will input x time -1, xt, and xt plus 1, and then it will output t minus 1 and t plus 1, okay? So this is a very quick review for the idea of recurrent neural network. Okay, so actually, recurrent neural networks are very hard to train. They will suffer from the saturation, the vanishing, exploding gradients. Yes, I think that is why LSTM comes out, because it wants to solve this problem of vanishing and exploding gradients, and its loss services are very complex, and it is very hard for them use some original dropout ideas. So LSTMs and GRUs address some of these issues, but they are not perfect. Actually, when you are doing homework 3 part 2 and homework 4 part 2, you will spend a lot of time tuning those hyperparameters, like the number of layers, or the dropout rate, or which dropout tricks you should implement in your homeworks. Yes. Okay, so actually, in the last slide, I will introduce one of those papers which should be helpful for to your homeworks. Okay, so let's introduce let's begin our recitations from 5 points. The first point is about the language model, and the second point is the RNNs in PyTorch. We will tell you guys how could we use RNNs modules or RNNs layers in PyTorch, and the third point is about how could we train RNNs, and the fourth is how could we generate text or generate outputs with those trained model. And the fifth, I think it is the most important one, is how could we use or how could we implement the variable length inputs. Okay, so let's first begin. Actually, there are a lot of tasks, right? As you can see here, there are 5 common tasks in NLP. The first is one input to one output. And the second task is one input, but there are a lot of outputs, right? And the third task is to use a lot of inputs and just output one, okay? And there are a lot of many-to-many like this, or many-to-many like this. Okay, so actually, the first task is about some linear mode of processing without RNN, from fixed size input to fixed size output, like image classification. Okay, this could be just like you are given, or your model is given one image, you have to predict its label. Okay, just like your homework 2. And the second task is about the sequence output. So usually, if you want to do some project about the image captioning, the input for this one-to-many should be just one image, and the output should be a sequence of words, because this sequence, this output, should be your captions, right? Okay, so the third task is about the sequence input. The input is sequential. It's like a traditional task, like sentiment analysis, where you are given a sentence. Each word or each character should be your input for each time, but you, at last, you need to classify whether this sentence or whether these characters express positive or negative sentiment. Okay, this is the third task. From many to one. Okay, so let's talk about the fourth and the fifth tasks. They are also about many to many, but they are a little bit different. Okay, so the fourth, as you can see here, the input and the output, they are not synchronous, right? Okay, so like the traditional task for the fourth task is about the machine translation, which means that after you read all those inputs, texts or input words, you could generate your translation. Okay, and the fifth task is about sequence input and output, just like the video classification, where we wish to label each frame of the video. Okay, so these are 5 traditional tasks, from one-to-one to one-to-many, and many-to-one, and many-to-many. Okay. Okay. So first, let's talk about the language models. Okay. So the goal of this language model is to predict the probability of a specific sentence. So, and actually, it just like it wants to predict the likelihood of the actual sentence. Okay, so here is just one quick image. So credits to this CS224N. Okay. Language models compute the probability of occurrence of a number of words in a particular sequence. It will calculate this P. It is a joint distribution of different words. For example, there are M words in your sentence, so the joint distribution should be PW1 and 2WM. Okay, and you will use this Bayesian equations to calculate this joint distribution. For each time, you will first, for example, if you want to predict this W1 first, then you will predict the probability of W2, the word 2, based on your previous outputs. So the second term would be PW2 given W1. Okay? And this approximation, just like the n-gram. Okay, and let's talk about an RN language model here. So, for example, the students opened there. These are your previous output. These are your inputs here. So you want to predict what is the next word. So as you can see here, this is the initial state of your RN model, and after you input these previous words, you will find that this is your distribution of your words. You could see there the books and the laptops could be the potential output. Yeah, maybe the students open their laptops or the students open their books based on different situations. Okay? Okay, so let's talk about how could we use RN modules in PyTorch. Okay? So here is a classic ARM model here. So just like convolution layer, we could just use nn.rn here. So the first parameter is the input size, and the second parameter is the hidden size, and the number of layers, batch first or not. Yes, okay, so actually in the default setting of PyTorch, it will not, specifically speaking in NLP tasks, it will use batch as the second or the intermediate dimension rather than the first dimension. So if you want to use the batch size as your first dimension, you should set this batch first to true, okay? And this is a built-in dropout, but I don't recommend that you guys use this because this dropout will be implemented in different layers rather than different time step. Okay, so there are a lot of other dropout tricks or regularization tricks in RN, like weight drop or variational dropout. You should try this. And this parameter is about the bidirectional or just one direction. So if you set this bidirectional to true, this RN will process your inputs from the beginning to the end and from the end to the beginning. Okay, it is bidirectional. Okay, so this number layers specify the number of stacked layers you will use in your model. And okay, so just like what I have talked about, so in the default setting, the forward method takes an input of size like sequence length times batch size times input size. Okay, so if you want to use the batch size as your first dimension, you have to specify the batch first is equal to true. Okay, and the initial hidden state, as you can see here, so this is your initial hidden state. So the size of the initial hidden state is number of layers times batch size times hidden size. Okay, so because if you just want to use the number of layers, so maybe this is just 1 times batch size times hidden size. Okay, but if you are using the number of layers which are equal to 2, maybe the initial state should be beginning with 2 here. Okay, so so ARM modules in PyTorch, I think there is a very important thing here we should care about is the outputs are exactly the hidden states of the final layer. So hence, if the model returns y and h, so here we talk about the ARM model. So the output of your model, the size of the output of your model should be like this. So the first dimension is about the sequence length. And if you do not specify the batch first equal to true, so the batch size is the second dimension. And the third dimension is about the number of directions times the hidden size. Okay, so this is your output. But there are another output which is called final hidden states. The final hidden states beginning with number of layers times number directions and batch and hidden size. So, so for example, let's set number of directions equal to 1. So the last element of these two guys are the same. Okay, so that is, so the last sequence of all the batch, and let's set this equal to 1 here. Is hidden size is equal to, this is equal to 1, the number of layers is equal to 1, and number of directions is, the number of directions is equal to 1, and the last layer, batch size and the hidden size, they are the same for this part. And there is a little bit difference for LSTM and GRU here, because LSTM will output two hidden states. The first is the hidden states, and the second is the memory cell. Okay? So actually, there is another module for RN here. It is about the RN cell. You might use this RN cell for much more flexible targets. For the difference between this RN module and RN cell is that RN cell you have to input. You have to give the input for the RN cell for each time, but the RN modules will automatically calculate all the time sequences. Okay? Okay, so the input of this RN cell should be batch size times input size. There isn't any time step here in RN cell, or you could understand this idea just like the RN module, which time step, whose time step is equal to 1 here. Okay. Okay, so next, let's talk about the embedding layers. Questions? Okay. So after the RN module, you need this layer, embedding layers. So embedding layers, okay. You need to specify the vocabulary size of your model and your embedding dimension. Okay. So actually, embedding layer, just like a projection layer, it will project your the space of your vocabulary size to the embedding dimension size, dimension space. Okay, embedding space. Okay. Yes.
So is this embedding layer before the final output? I think that you have this embedding layer just before you output the data, right?
So which actually, there are a lot of different tasks, right? So I could not safely say that you have, but commonly we will use this embedding before your models. Yeah, I think Hannah will introduce more ideas about this embedding layers in the Jupyter Notebook part. Okay, cool. Okay, so next, let's talk about how to train a language model. Okay, so just like what you guys have learned in the previous tasks, like convolutional neural networks and MLP. So you need use these batches to feed your model. So let's talk about the simplest way first. So the input of your model should be just like a fixed sequence, and which the length of this fixed sequence should be equal to L, and you need to concatenate all your words into one big long tensor and divide it into n divided by L tensors of size L, and these are your elements. Okay? Oh, sorry. And then let's talk about how could we evaluate our model. So actually, there are two criteria you could use in NLP tasks. Of course, there are a lot of different evaluation methods and criterion for different NLP tasks. But here, we just introduce two common criterion. The first is the loss, and the second is the perplexity. So the perplexity will quantify how well your model predicts that sentence. If a perplexity of 100 means that your model performs as if it had to choose uniformly rather than some very good distribution among these 100 probabilities for each word. Okay? Okay, let's talk about this generation task. Okay, in order to generate n words, you have this n times vocabulary size possible sequences like this. Okay, just like what we have mentioned in previous slides. So here it's just like a language model. Okay. Okay, so then let's talk about these three methods of search. Of course, there are a lot of other search methods like A-star search, but here in our recitation, we just, or in your homework 4 and homework, okay, just homework 4, you just need to use these three methods of search. So the first is about the greedy search. Okay, so the greedy search will help you select the most likely word. Okay, and the random search is about how to sample a word from the distribution. Okay, and the beam search will always keep the n best words at each step. N is the beam size. Okay, I think in the future slides about CDC and attention, Li Wei and Ethan will introduce more ideas about the beam search or the beam search. Okay, so today in our recitation, we want to just give you guys a very quick idea of these methods. Okay, so are we done? Okay, as you can see here, there are a lot of, almost half of the slides, so yeah, actually we are not done. Okay, so yeah, so actually just like I have mentioned, we could train our language model based on the fixed length. So here, so first we will concatenate all our words into one big tensor of size n and divide this tensor into different tensors by this size L. And this would be my different instances, and I could use these different instances as my batch. But here, we have a lot of limits. Because in machine translation or speech recognition, you have pairs of sequences. For example, if I want to translate "I like apples" into, is this French or Germany or? Oh yeah, French. I'm sorry, I don't know how to spell the French sentence correctly, but I will try. J'aime les pommes. Okay, so I need to keep these sequences as is to learn something, because the sequence, this sequence, for each of your sequence, the lengths of this sequence are not the same. They are not fixed, right? So we are not dealing with any of these specific applications today, but to learn RNs, you need to learn how to deal with variable length inputs. Okay, so let's talk about how could we deal with that idea. Okay, so how could we train the language model based on variable length? So here, my data set is now a list of n sequences of different lengths. The input has a fixed dimension. It's like this. The first dimension is the sequence length, and the second is about the batch size, and the third is about the input size. How could we deal with this situation? The first method we could use is this paired sequence. And the second method is this packed sequence. Okay, so here is a quick example, and Hannah will introduce more ideas about the padding sequence and the packed sequence in the Jupyter notebook. So first, you need to import this paired sequence. For example, so x1 is equal to 1, 2, and the size of x1 is equal to 1, 2, and x2 is 4, 2, and x3, the size of x3 is here like 3, 2. So for each instance, their input size are the same. Okay, their input size is still here, but their sequence length is different. So for x1, the sequence length is 1, but for x2, the sequence length is 4. So if you want just use this torch-stack to stack all of these 3 tensors, it will tell you the sizes of tensors must match except in dimension 0. Okay, so we could not generate a batch of different instances just like the previous tasks. So how could we deal with this situation? So first, we could use the path sequence. So here, the path sequence, so the input should be your sequences with variable lengths, and you have to specify the batch first is equal to first. If you, the batch first is equal to false if you want to generate a sequence length beginning tensor. Okay, so here. Okay, so this is the output of your path sequence. Okay, so actually, when I see the output the first time, I feel I feel very confused because I'm wondering why those zeros are here rather than the other dimensions. Okay, the idea is that because the batch is on the second dimension, so here we have to comprehend this padded sequence like this. Okay, so the first sequence is this. Because x1, the length of x1 is equal to 1. So the padded x1 should be 0.6195 and 0.4712. And this 0.0, 0.0, 0.0, these 3 parts of the first element are the padded parts for x1. Okay? And the x2, which is the length of x2 is equal to 4. So we could see that the first element, there isn't any padded 0 here. And the length of x3 is equal to 2. So these are the 2 first elements for x3. And the length of x2 is equal to, 3, So as you can see here, so these first 3 elements are from the original x3, and this 0 is padded here. Okay, because you have always need to remember is your batch size is your first dimension or your second dimension. Okay, this is very important. Okay. So next, let's talk about the pack sequence. Yes, actually, there are a very quick shortcoming here in path sequence because this 0 information, we could not use this 0 information, right? Because they are not from the original sequences. You have to eliminate those padded parts. Specifically speaking, when you are dealing with the homework 4 part 2 sequence-to-sequence model, you have to mask those zeros yourself before you calculate the attention scores and calculate your final loss. Okay, so I think in the attention recitation, you will be introduced more ideas about the masked sequence. Okay, and here is another method to solve this problem. Okay, so actually this method is called pack sequence, and there is a very important parameter here, which is called enforce sorted. Okay, so when you set this enforced sorted is equal to true, you have to you have to beginning from the longest length of your sequence. But if you set this enforce sorted to equal to false, you could pack the sequence without setting the first sequence to the longest one. Okay? And this is the output of the packed sequence. Okay. Let's talk about what is the meaning of the batch size, the sorted indexes, and unsorted indexes. Okay. So, so the definition of batch sizes. So the definition of batch sizes is that for each time step, how many tensors your RNs would process. Okay, so as you can see here, the batch sizes of this is equal to 3, 2, 2, 1 here. Okay, okay, it is here. So the batch sizes is about the tensor of integers holding information about the batch size of each sequence step. For instance, if the given data is A, B, C, and X, and after you pack this sequence, this packed sequence is about AX, B, C. So in the first time, it will process AX simultaneously, and then it will process B. And then it will process C, because here ABC is a sequence and X is also a sequence, so you have to process the first elements of those sequences simultaneously. So that is the idea where the byte size, why the batch sizes is about 211. Okay. Also, we could convert the padded sequence to the pack sequence by padded sequence, and of course we could convert the packed sequence to the padded sequence by packed sequence. Okay, yeah. So these two methods are really hard to pronounce correctly. Yeah, padded sequence and packed sequence. Okay. So for the packed sequence and RNs, the packed sequences are on the same device as the padded sequence. And these packed sequences could help you RNs know the length for each instance. As you can see here, for this packed sequence, there isn't any paddings here. So the paddings will not have a big impact on your RN models. Okay? So otherwise, you have mask them by yourself. Okay, so then let's talk about the ideas of NLP and RN and CN and transformer. So you will learn more about transformer in the future recitations, but here I want to just give you guys a quick comparison about these different layers. Okay, so when you take a look at the documents of the PyTorch, you will notice that there are nn.dense or nn.linear and nn.rn, nn.lstm or GRU, and nn.convolution 1 dimension, 2 dimension, and of course the transformer. Maybe my favorite models. Yes. Are they different? they are a little bit different. But all these layers are just features extractors. And some of those ideas might borrow from this, and those ideas could be used into some sequential decision-making problems. But here, traditional speaking, we could not use this directly to some sequential decision-making problems. Okay? So in this paper, an empirical evaluation of generic, convolutional, and recurrent networks for sequential sequence modeling. I think this paper was written by one professor from Carnegie Mellon University. His name is Coiter. So in this paper, the authors argued that the temporal convolutional network outperform almost every recurrent network, such as LSTMs, across a diverse range of tasks datasets, while demonstrating longer effective memory. Yeah, this guy might argue that you might not know the really idea of LSTM. Okay. So let's compare the RNs and CNs here. Okay. So RNs would process input sequentially. So here, so the first time you will input the embeddings of the word the, and it will calculate the hidden states with its initial hidden state. And the second time step, you will input the country here. Okay? The RN is like this, but for CN, it is like this. So the CN will calculate the country, and then country of, and of my and my birth. Okay? So CN could compute vectors for every possible phrase. Okay? Actually, you could use the combination of CNs and RNs in your homework 3 part 2. Is that enough? Actually, no. Yeah, because in this paper, the attention is all you need. So actually, in this paper, the Google first introduced the idea of the transformer. Yeah, so actually, you guys might hear a lot of terminologies like BERT or LXNet. Actually, the BERT and the XLNet are based on the idea of transformer. And in this paper, attention is all you need. They are very cool table. Is here. So if the layer type is self-attention, the complexity per layer would be n squared times d. But if you are using the recurrent layer type, the complexity for your layer is equal to n times d squared. Okay? So the n is the sequence length, and d is the representation dimension, and k is the kernel size of convolutions. So here, if you are using the convolutional layer, the complexity of your layer is like k times n times d squared. Okay? And so if you are using a restricted self-attention, the complexity of your layer should be equal to r times n times d here. Okay? Okay, question?
What does it mean by restricted self-attention?
Oh, yeah, okay. So first, I strongly recommend that you could read this paper, okay? And yeah, because we have not covered attention yet in our lectures or in our recitations. So here I want just give you guys a very quick introduction about these ideas. Okay. Yeah, so maybe in the future, you could learn more about the attention, self-attention, or other attention, multi-head attention from lectures. Okay? Okay, so the final slide is about the papers, the reference, and yeah, the attention is all you need. And yeah, just like what I have mentioned at the beginning. At beginning of the slide, so job your RN and LSTM, they are not good. You might wonder why does this sentence make sense? Yeah. So here is a very this blog is very good. Okay. I strongly recommend that you should read this. And this paper, attention is all you need. Actually, this might be my favorite paper. And also, if you want to learn more tricks about the regularization and optimizing LSTM language models, you should read this paper here. Okay, so this paper is written by So in this paper, the authors, so this paper was written by the Salesforce Research, and in this paper, it introduced a lot of ideas about the weight, job, LSTM, and the optimization part, and like this ASGD and weight tying, which is very important for your homework for part 1. And like this, variational dropout. Actually, this dropout should be better than original dropout tricks. Okay. Yes. So next, Hannah will introduce more ideas on the Jupyter Notebook. Okay.
Okay, so we'll go over some of the implementation basics of RNNs. We'll be looking at LSTMs being used for a fixed length model, like Carnegie mentioned, and then also using the pack sequences for variable length inputs. So we have a text corpus here, and all of this will be available on the website after the recitation, where the corpus is this Shakespeare data, some book or some sonnets. And basically this is for you to get an idea of what the data looks like. And here we prepare our data set. We're first looking at the fixed length input, and we're doing a character-based model. So we'd not be predicting the next word, but the next character, and generating a sequence of characters. So as you can see here, we are setting the sequence length to 200. And breaking it apart in those forms. This is not taking into consideration any full stops, any ends of sentences. This is just saying this is your entire corpus, split it up into sequences of length 200. And you can obviously see where this is an issue, because you're losing a lot of information about your text by doing this. So we also have a collate function. I'm sure in the previous homeworks you've already seen custom collate functions when you're defining your data loaders. And this is basically just allowing us to format it into the correct shapes and lengths of the sequences. If you see here, this function unsqueeze, this is similar to the NumPy new axis function, which just allows you to add a new dimension as needed, and then you can populate it by your multiplications or your tensor operations. So here also, as you can see in the get item, what exactly counts as the input and output in this kind of model? If you have a sequence of, suppose, 10 words, then your output is going to be also a sequence of, so your output will be that same sequence, but your window is shifted over by 1. So if you had a sentence that said the cat is brown, and your first window is the cat is, then what you want to predict is brown, right? So what's your output? Your output is that entire sequence shifted by one, so it would be cat is brown. And brown is the word that you're outputting. So that's what we're doing over here with the indexing over here. Because we're saying that up until the last character is our input, and then the output is excluding the first one up until the very last one, including the last one. And this will come into play in your homework 3. So you'll have a similar structure for homework 3. Now we're defining the model itself. And as you can see, so Carnegie mentioned the embedding layer. So we have the embedding layer comes in over here. It's normally before your RNN layer. So what the purpose of the embedding layer is for you to basically have a feature representation. So because your inputs are right now just indices mapping to your characters in your vocab, but that's not that doesn't contain much information. So you have this embedding layer, which is a built-in PyTorch module, and what this does is it generates like a representation based on your vocabulary size. So this is the output of this is what you would feed into your LSTM. So the basic structure of any language model is you have a embedding layer, then you have your RNN, and then you have your scoring layer. Excuse me. Your scoring layer is basically your linear classifier, as you've seen it in your previous homeworks. So it's basically going to transform your outputs into a sequence of probabilities corresponding to your vocab size. You could think of it as the inverse of your embedding layer, because it's basically doing the opposite version, going from your representation to your probabilities based on the vocab. In our recitation, we are using the LSTM module, but you are also more than welcome to try GRUs. The syntax is almost the same, but don't take my word for it. Check the documentation every time you're implementing something. PyTorch also has nn.rnn, but that's the basic RNN module, and we don't suggest using that. LSTMs and GRUs have been developed to solve the problems, as Carnegie was mentioning, of vanishing gradient, exploding gradient, and a number of other things. So depending on your task, you might want to use LSTM as opposed to GRU, but definitely we wouldn't recommend starting with the basic RNN. Yep.
Is the embedding layer trained?
So the question was, is the embedding layer trained? I believe it's not trained. I think you can, Carnegie, correct me if I'm wrong. Carnegie?
Yes.
Do you know if the embedding layer is trained?
I think actually you could specify.
You could specify,
whether,
yeah.
Yeah, embedding layer is trainable or not.
So by default, it's not. But I believe there's a way that you can decide to like train the embedding layer itself as well. Actually, let me check and I'll get back to you because I'm not sure. Because I think since in the forward it is going through the entire backprop, you backprop through your embedding layer, I think it does get trained. But I know there's another like caveat to it, so I'll check and make sure.
But in this, you're not using like any Siva or Kickdown embedding, right?
No, this is, so I don't know what PyTorch does internally. It might be defaulting to one of those, but like not explicitly, no. So the thing is, it's basically you want to increase the dimensionality of your vocabulary. Like just the index mapping is not enough. But now that I'm thinking about it, I'm pretty sure it is trained, but I'm going to confirm and let you know. Yeah.
I have a question about the scoring.
Mhm.
Scoring layer. Is it true that the scoring layer would share some sort of similar
To the embedding layer.
with like embeddings with the embedding layer? Because like you need to do the embedding to convert it into like machine things that machine knows, and then kind of the scoring layer does the opposite to it. That's what you just mentioned.
Yeah.
Do they share kind of the same knowledge
Okay, I'll just repeat your question and then I'll answer. So the question is, does the scoring layer share any knowledge with the embedding layer, since they're basically doing the inverse operation? They don't, architecture-wise, they don't share any information. The scoring layer is a linear layer. And the idea is that as you can see over here, your embedding layer takes vocab size and then embed size. And then this is taking hidden size to vocab size, not embed size to vocab size, because you have the RNN in between. So you can think of it as the embedding layer is translating your data set ready to input to the LSTM, and then your scoring layer is translating the output of the LSTM for you to be able to infer from it. Yep.
Yeah, actually, in the paper, yeah, there is idea of the weight tying. So if you are doing weight tying, you will specify the embedding size is equal to the hidden size, and you will tie the weights of the embedding layer and the scoring layer.
Okay.
Just like you could implement, or you could get more ideas of these tricks in that paper. Okay.
Yeah. So Kanguri was just saying that the weight tying method lets you do that tying that was mentioned between the scoring and the embedding layer, and that's in the paper that's referenced in the slides. So we'll go and look at the forward and the generate. So here, as you can see, is we're initializing hidden to none. You could come up with or look at some papers as to how you want to initialize your initial hidden states, the same way you maybe initialize your weights and your biases. But PyTorch by default initialize the matrix to all zeros if you don't specify. And if you see here, we have a tuple being output when we do RNN forward. This tuple is the output of your LSTM, and this hidden here is actually another tuple, which corresponds to your hidden state and your cell state at the end of that LSTM. So what these are for is if you wanted to feed this forward into another RNN component, then remember I said right now hidden is none. You could pass in the hidden state from this output of your RNN if you were to be propagating it forward to another component. And then we are just flattening the output to be able to feed it to our scoring layer, to our linear layer. And then this is going to give us the probabilities. And as with all of the homeworks, you must have realized by now that if you get your shapes right, you're almost always like on the right track. So it's really important to keep track of your shapes. As Kanguri mentioned, by default, RNNs do not take batch sizes first. So if you notice over here, we have L by N by H, where L is the length of the sequence and N is our batch size. So batch size is at dimension 1, 0, 1, 2. So that's just something to keep in mind because it's something very easy to forget and then hard to find when you're trying to debug. And you could always set the flag for batch first equals true, but just keep in mind what steps you are taking. So in the generate function, this is where we're trying to generate the next character. Or in other scenarios, it might be the next word. So suppose we wanted to complete a sentence, right? So over here, we're setting n words, number of words that we want to generate. So we loop over and generate that number of words. What the generate over here is doing, just by the way, the logic up here is the same as the forward. But what we're doing is when we get the last output, we feed that back in because we want to generate a sequence. And as I said, think of it as the shifting window frame. So if you have the first two words and you predict the third word, now to predict the fourth word, you don't, these become less important. So you shift over. And with the fixed length sequence, you're basically implementing the n-gram method, which is that there's heuristics to figure out what length of window you're looking at. But with RNNs, you technically have infinite memory. So that's kind of where the power of RNNs comes in, where you can abstract this n out to be, you don't have to specify this window. Does that make sense? So this is just your training epoch over here. This is the same as in the other models, MLP, CNNs. What I wanted to highlight the pack and padded, 1 second. Oh, sorry, that's in the next one. Okay, so this is just basic updating your optimizer, setting your loss. You'll notice here that we are also using loss, and we're using this measure called perplexity. Perplexity is the same, definition-wise, it's the same as the English word, where it's your level of confusion, let's call it. So perplexity measures how unsure your predictions are. And perplexity is, you can see it's the exponential of the normalized loss. So it sometimes helps you when you're training because it'll show you more differences than your loss might. So your loss might be decreasing slowly, but your perplexity will be going down faster. And then you can tell, like, okay, your model is doing the right kind of thing. And it's like the calculation is just this translated into math. So if we now look at so there are a bunch of examples here which you can run and see. You'll see that, I don't know why this hasn't finished running, but you'll see that when we generate over here, you'll have a lot of words and repeated. So it's basically for you to be able to see the relative differences between the character, the fixed length model and the packed sequence model. You'll see when you have the notebook online that the results with the packed sequence are a bit more logical and what you would think would come out. But also bear in mind that this is a Shakespeare text-based model. So if you were to put in something more like conventional English these days, it would probably give you worse results. So keeping in mind the data set that we're using. So now if we look at the packed sequences, take a note right now of the fact that we're defining the stop character and the space character. So the space character is just for like processing, but the stop character will be important lower down when I show you the training and the model. So this is just like the pre-processing of the lines of the data. And then where's our... So here's the data set for the packed language model. Now, just to clarify, RNNs take in packed sequences. So they allow you to feed in the sequences of different lengths, but they require them to be, by default, they require them to be sorted in descending order from longest to shortest. Kanguri showed you in the slides that you can set that to be false. But then you have to take into consideration the indices specified in there's a feature of it which says what is the index of them. I would suggest just sorting them in your data set because then that reduces the headache later on when you're later on in your model. So that's exactly what we're doing here. We are sorting them by length and returning them in that order. Does that make sense? So when we look at the model itself, and then you can see, that the input-output is the same idea, shifting over by 1. That doesn't change. The only thing that changes is that now you're giving in sequences of variable length, and those need to be sorted in descending order. So we still have the same structure. We have the embedding layer, the LSTM, and then the scoring layer. And then over here, so there are multiple ways, by the way, of doing the things that we're mentioning here. Even in terms of the functions that are available to you, there's the pack sequence, pad sequence, pack padded sequence, and pad pack sequence. So the names themselves are pretty self-explanatory. If you just have your, I'll show you here. So since we only have the inputs from our data set, these aren't padded, right? You saw in my data set I wasn't padding anywhere. So what I'm going to do before I can pass it to my RNN is I have to pack it. Suppose I had decided to pad in my data set, Then what I would be doing before passing to my RNN is I would be doing pad pack sequence. Now, there are preferences on what you do. There are things you need to keep track of, because when you pad, you need to keep track of the lengths, right? Because those lengths, like Kingri said, you don't want to be adding noise. That's the main reason that PyTorch RNNs have been developed, to not take in padded input, to take in variable length input. So if you had that, then when you do pad pack sequence, that gives you the lengths as well. So also be careful, like a lot of the times you'll be trying to access a variable and it'll say, no, this is not a variable. Like you might have a tuple. So always just check the documentation, because especially with RNNs, a lot of things will give you a tuple of the different pieces of information. Mm-hmm.
So you mentioned that we need to keep track of the length, but when you pad, like each batch would have the equal length, right?
So each batch would have, so the question was, why do we need to keep track of lengths when we're padding? Each batch will have the length of the longest sequence in that batch, but when you need to keep track of the lengths of the actual sequences, because you don't want to take into consideration the padding elements in your.
That's for indexing, right?
Yes. So over here, we are specifying, so because we didn't pad, we are over here specifying the bounds. So we're specifying the start and end of each of our lines and of our sequences, sorry. So because we had concatenated. Yeah. So, sorry, this is before we concatenate, because we would lose that once we concatenate. And then we are doing the same thing where we pass it to our RNN, and we're passing it the packed input. You could also just not specify this, and this would not cause an issue. It would default to knowing that it's not been defined. So if we look over here, because we passed a pack sequence, we need to get back a padded one, because a linear layer cannot take a packed sequence. The linear layer needs equal-sized inputs. So what we have to do is we use rnn.pad pack sequence. So do you see the logic here? We couldn't just use rnn.pad. Or we could, but you would have to do a little bit more from your side. Here, because we are getting a pack sequence out of the RNN, we can directly say, I want to pad my pack sequence. But if you were to be padding in your data set, as I mentioned earlier, then you would use RNN pad sequence, because it's not been packed yet. So an RNN always returns you a pack sequence. So we convert this to padded, we flatten it, so that we can put it into our scoring layer, our final linear layer. And the generate function, again, it's the same logic as before. I mentioned, and this will be important for homework 3, or homework 4 maybe even, I highlighted the stop word, the stop symbol. By the way, these are all mapped to indices. The model cannot take just strings. So part of the data set is mapping your characters or your words to your indices and your vocab. And those indices are what are embedded by the embedding layer. So if you see here, the RNN, because we didn't specify a sequence, it might, you might be generating past the full stop. But that's like the end of your sequence. So suppose a sentence makes sense to stop at a point. If you were just to loop over your number of words that you had decided to generate, you might be generating garbage values after. So it helps you to be able to check that if the current word you produced is the stop word, then you can just break out of your loop. Because a logical sentence is the sequence that we're looking at. So if you have a stop word, and then you can modify this, you can add question marks as part of your stop words. So it doesn't have to be just a full stop. And this is a heuristic in a way. And you'll see this will make more sense in the context of the homeworks, homework 3 and homework 4. So the training is, there's not much difference in the training. I don't think there's any difference in the training. And again, we're looking at the loss and the perplexity. And if you were to see, So just to note, this sometimes is confusing. We mentioned that we want to sort by sequence length in our data set. In our data loader, we can still shuffle. That doesn't cause any problems because the shuffling, when we say shuffle equals true in the data loader, what that means is shuffle the things you're reading from the file. And then, so the way the process works between the data loader and the data set is that when it reaches the data set, it tells it how to access the things. So when you say shuffle equals 2, it shuffles the things, gets a batch of size 64 in this case, and then figures out how to get those items using the get item defined in the data set. So if you are sorting, that's fine. Each batch will be sorted already. The shuffling is not going to happen after what you've defined in your data set, if that makes any sense. Is that clear? Yeah. So it's before that. So your sequences will be in the order that you defined. So like I said, I'm sorry I can't show you the actual results, but when you see, it is a bit better. Actually, this is a very basic model, but you can already see the difference between using the fixed length sequence and RNNs with the pack sequence when you will see the results of these generations being output. And then these are just some final reminders that I added for your reference. They're a bit of a repetition of the slides, but it doesn't hurt to have it there as well. So batch first equals false for RNN modules. And to use pack sequences, you must first sort your inputs into descending order of length. Are there any questions? Yes.
Just wondering, is there a reason for the descending order of length?
It's a design. Maybe there's an internal thing that becomes more efficient by having them descending, but I don't know if it. Yeah, I think it just makes it easier for PyTorch to internally do the padding because it knows the sequence lengths and it knows them in order, so it just has to look at the first one to figure out what's the longest, and it pads all the rest of them to that. That's what I'm thinking logically, but there might be a different reason. Sorry, and the question was, is there a reason for it to be in descending order? Yep. Any other questions? So the other things that were mentioned, like the CTC loss and the beam search, they'll be covered in the next coming up recitations because you've only started looking at RNNs in class and you're still working on homework too. So the more technicalities of those will be in the next week's and the following week's recitations. Is there a question?
So like when you said like descending order, it means like your input would be one huge sentence, right?
Mm-hmm.
But then wouldn't the context change like when you start?
No, so what do you mean by the context?
I mean, say if the character is brown,
Mm-hmm.
brown might come at the top and then that might be
No, so the question is, if we're talking about descending order, how is that maintained if you have like the order might change? So I think you're just mistaken. And so when we're talking about word generation and even in character generation, the order is maintained, and that's the power of LSTM. So it wouldn't, the order of the words is not changed by shuffling. What your input data set is a text corpus, right? So what you do is each sequence is, you could say it's a line in your corpus. So you shift that over. So there is never an instance where the second sentence will be before the first sentence, right? Like if it is, that sentence's label is that sentence shifted over by the window. Do you understand? So that maintains the order.